Right, let's continue from where we've ended up. Remember that we did the equation of a tangent and how to find the equation of a tangent. So today we are going to look on how to sketch a cubic function and how to interpret it and all those things. But then we need to understand first, what is a function? When we talk of a function, it's something like that. It's where we are going to look on what happened to y if x is increasing or decreasing. So that's what a function tells us about. So today we are going to look on a function that we call it a cubic function. Remember that we said a cubic function is called cube. So it's ax cubed plus bx squared plus cx plus d. That's a cubic function. So here we've got all those letters. As you can see, we've got f at x, which represent y. This is our y. F at x is our y. And then we've got x. X is the same as that one. All those values represent x. And then there is a most important value here, which is a. The value of a determines the shape of the graph. It determines the shape of the graph. It tells us about the shape of the graph. And then, again, we've got that value of d. When you look here, that's the only value that doesn't have x, which means if you do not have x, you only have d. That will mean it's where your graph will cut y, because this will mean that y is equal to d if there is no x. Therefore, for you not to have x, that means you are going to have 0. That is f at 0. So if x is equal to 0 here, that will mean your f at 0 is equal to d. And then I will show you what does this mean. The most important thing, as I said, here is the value of a. There are some different shapes of this kind of graph. This graph, you might find it, as you can see, it has got 3 up there. So it's a cubic function or a cubic polynomial. Therefore, it has got 2 turning points. It has got 2 turning points. It might be looking like that, or you might find it on this shape. Again, it still have 2 turning points, but not that it must always have 2 turning points. You might find out that your graph is looking like that. This is still a cubic function, but with no turning point, as you can see up there. Right, let's look on the shapes as it is. Right. We've got this part here. When you look at it, the graph is going up here. And again, the graph is going up there. If you can put the sign there. So we've got 2 parts where the graph is going up. That means it is increasing here. It is increasing. So this is the only part where the graph goes down. It increased twice, it goes down once. Therefore, we are going to call this function an increasing function, because it increased twice, it goes down once. This is an increasing function. Increasing function. Right. Let's look at this one. Let's check if it's an increasing or decreasing. Here it goes down, as we've said. Also, goes down there, it goes up here. So when you count here, it's 1, 2, it goes down, and only one way it goes up. Therefore, this would be a decreasing function. It's a decreasing function. Right. It decreases, and then here it increases, and then here it decreases. Right. Each of these points in a graph, each of the point in a graph, it has got its name. Right, when you look at this one here, there is that point there, and also that point. We said when you move from this way to that direction, you are going upward. So when you reach this point, the graph doesn't continue. It stops and goes down to that point. And then up again. Up, up, down. Therefore, since we are saying this point is at the top, we call it a local maximum. It's a local maximum. This would be local minimum since it faces upward. That's a local minimum. Right, and again, remember that we are saying this side, the graph is going up. If you are to talk about a tangent, remember that a tangent has to touch the graph any point here, once. Therefore, when we talk of a tangent, this side, it goes up. Also here it goes up. Which means the tangent here, since it goes up, its gradient will be positive. Remember that we spoke about a function, and then we said this is a gradient. This is a gradient of a tangent to a function. Let's name this function as the function of f. Right, the gradient here on this side and that side, since the graph is going up, the gradient will be positive. If something is positive, that means it is greater than 0. Again, the graph is going up here, therefore, its gradient is positive. It is greater than 0. We are talking about the gradient. The gradient touches the graph at one point. So when you look here, if you are to put a gradient, it will be like that. It's like a horizontal line, like that. It touches this graph at one point. This point, we call it a stationary point or a turning point. This is a stationary point. I said the graph stops at this point. So therefore, we call it a stationary point. This is a stationary point or turning point. Right. So that line there, it tends to be horizontal. We call it a tangent. So the gradient of a horizontal line, since we are saying it's a horizontal line, that is 180. Therefore, its gradient here will be 0. The gradient of a tangent at the turning point will be equal to 0 at the turning point. So let's look here. We are saying, since this is a stationary point or turning point, the gradient is 0. Also here, the gradient is 0. At the stationary point, because if we are to put a tangent, it will give us a horizontal line. So the gradient of a horizontal line is 0. Right? And again, we are saying from this side to that part of a graph, the gradient is positive. It's positive. So this is the gradient. Gradient. But here, it's negative. The gradient is negative. The gradient is negative. It's negative. Also, here, the gradient is positive. When you're talking about the gradient, it's negative here. Because the graph is going down, the gradient is negative. Right. We were looking on how to interpret this in terms of a gradient. Right, let's now look on what happens if now we are having what we call the x-axis, because the graph has to have the y-axis and the x-axis. Right, let me draw the Cartesian plane. Right, we call that a Cartesian plane, right? So, let's draw an increasing function. Right, let's say this is the function of g. Right, when we look here, your graph now, in terms of the axis, it cut x there, it also cut x there, and also at that point. Let's say this is point A, point B, point C. So we've got 3 points where the graph cut the x-axis. So we call those points the X-intercept, because it's the point where the graph cut the x-axis. So point A, B, and C are the x-intercept. These are the x-intercept. Again, remember we've got the set of axes, which is the x-axis and the y-axis. So only that point where the graph cut the y-axis. Let's say this is point D, this point here. That's point D, point B here. Right. We've got only one point where the graph cut the y-axis. So point D will be our y-intercept. Y-intercept. It's where the graph cuts the y-axis. Right. The points where the graph cuts the x-axis, those values of x at those points, we call them the roots. The values of x from point A, point B, and point C, we call them the roots. Therefore, which means we've got how many roots? We've got 3 roots. It's A, B, and C. X at A, X at B, and X at D. Those are the roots. Right, we spoke about the stationary point, the x-intercept, y-intercept. Right, when you look at the 2 curves, at this curve, we've got the curve that is facing downward, like that. Right, we also have this one here, that is facing upward. So if you combine the two, they will give us a cubic function. So there is this point here, this point, that point there. Let me remove this point again. The graph, this graph here, it's concave down. It's concave down. Whereas here it's concave up. Right. It's concave down, concave up. So at this point, remember this is concave up, and concave up will meet that graph of concave down here at this point. So the point where the two meet, we call that point a point of inflection. That's a point of inflection. Point of inflection. So now we've got the following points. We've got a point that we call it the y-intercept. A y-intercept. Number 2, we've got x-intercept. Number 3, we've got the stationary point. It's a stationary point or turning point. Stationary point or turning point. And then, now we are talking about this point here. We call it the point of inflection. The point of inflection. Right. The y-intercept is a point. It's a point. So it is a point where the graph cuts the y-axis. The y-axis is a point. It's a point where the graph cuts the y-axis. So in a graph, if it has to cut y, it will cut y once only. Right, so this is our first point in a graph. The second point are our x-intercepts. The x-intercept are the points where our graph cuts the x-axis. Points where our graph cuts the x-axis. We call them the x-intercept. And then we've got this point, which is the stationary point or the turning point. That's our turning point. Also, that is a turning point. Let's say this is point E and point F. Point E and F are our stationary points. And then again, we've got the point that we call it the point of inflection. The point of inflection is this point. It's a point where the graph changes its concavity. It changes its concavity. Like, for instance, here it was concave down. At this point, it's where it started to change to be concave up. So it's a point where the graph changes its concavity. Right. So these are the points that we need to have before you sketch your graph, if you are to sketch the graph. And then we spoke about A here, which will tell us about the shape. So if the value of A is positive, if the value of A is positive, let us remove this. So if the value of A is positive, that's how your graph will be looking like. A is positive. So if A is negative, the graph will be looking like that. So these are the important things that you need to consider before you start sketching a graph. You need to look at the shape. You look at the value of A, oh, the value of A is positive. My graph has to increase. The value of A is negative, it has to decrease. So those are the important things that you need to consider before you start sketching your graph. Right now, let's look on how to sketch or to find each of those points. Remember, we've got the y-intercept, the x-intercept, the stationary points, and the point of inflection. Right, for y-intercept, in order to find the y-intercept, let us write our function. It's ax cubed plus bx squared plus cx plus d. Right. Remember, we are talking about the y-intercept. The y-intercept. The y-intercept. The y-intercept is a point where the graph cut the y-axis. So, how many points where the graph cut the y-axis? Only one point where the graph cut the y-axis. And when you look here, it's the y-axis. So, that means x is not included. It's only y because it's the y-axis. There is no x here. Therefore, x is 0 here. X is 0. If you are to write the coordinates of the y-intercept, x will be 0, which means for y-intercept, we let x to be 0. For y-intercept, we let x to be 0. X to be equal to 0, which means you are to find the remainder if x is equal to 0. So it's a into 0 plus b into 0 plus c into 0 plus d. So it's a times 0, b times 0, c times 0. That's 0. Therefore, our answer or our remainder if x is equal to 0 will be equal to d. That's our y-intercept. Our y-intercept. Our y-intercept. 0 is to d. When we talk of a point, let's say for instance we've got point A point must have two values. It's the value of x and the value of y. So it's x is to y. So here, to find this point, x must be 0 in a given equation, and then you find the value of y at that point. Right. The next point that we have there are the x-intercept. The x-intercept. X-intercept, we are talking about the x-axis. So obviously, since we are talking about the x-axis, there will be no y. It's only x there, only x, no y. Therefore, since we are saying there is x here, y is here, there is x here, therefore, there is no y here. Which means, since we are having 3 points, let's say this is point 1, it's point 2, 0.3. It's 0.3 here, which means we are going to have 3 values of x. x1 is 2, remember that, and y is 0 there. Again there, we are going to have x2 is 2, 0. There again, we are going to have x3 is 2, 0. So we are having 3 values of x. If this was the function of g, that will mean we are going to have this equation here. It's a, which tells us about the shape, x minus x1, that value, x minus x2, x minus x3. So x1, x2 and x3, these are the x-intercept. These are the x-intercept. Right? There is x there. X times x is x squared. Times x, it's x cubed. That will give us a cubic function. It has to be x cubed. Therefore, that x is not as the same as x1. It's not the same as x1. x3 is not the same as x. So we've got x, we've got x, we've got x. That represents one value of x. Therefore, this x here is any point. This is any point in a given function. This is any point in a given function. Right. We also have, this is a function of g, therefore we've got g there. G again. This is any y value of a given point. This is any y value of a given point in a function. Right, which means g and x are together. Therefore, this point will say x is to g at x. X is to g at x. Any point here in this graph, you can call it x is to g at x. Any point, it can be either here, that is x is to g at x. When we say x is to g at x, it's because g at x represents the value of y. It's the value of y. Right. That's how to find the x-intercept. For x-intercept, we have y to be 0. That's the reason why we are having x1, x2, x3, and then our a tells us about the shape. Right, the next point we spoke about is this point, which is our turning point. Which is our turning point. In a function of g, since we have said that function is a function of g, in a function of g, if you are to write this equation in a standard form, it will say ax cubed plus bx squared plus cx plus d. Right, in order for us to find this point, the turning point, we will have to derive. Meaning, for turning point, we derive. As driving, we derive. So, g, you derive the function of g to find the gradient. This will be 3ax squared plus 2bx plus c. We are deriving the given equation. So remember that a derivative, it's a gradient of a tangent to a function. A gradient of a tangent to a function. So we are talking about the gradient of a tangent. At this point, the tangent has to pass there. It has to pass there. So this is a horizontal line. It's a horizontal line. Our tangent will be a horizontal line. Therefore, the gradient of a tangent at that point is 0. Which means, for stationary point, you will have to derive. Remember that a derivative is a gradient. Gradient of what? Of a tangent. So the gradient of a tangent at that point is 0. That's the reason why you have to let the derivative. We let our derivative, which is our gradient, to be equal to 0 because this is a turning point. So 3ax squared plus 2bx plus c will be equal to 0 at that point. So now you can be able to solve for x after letting that gradient to be 0 because you only have now x. And then that means after letting the derivative to be 0, you'll have to factorize since this is x squared. You'll have to factorize to find the values of x at a stationary point. You factorize and then after you solve for x. After letting the derivative to be 0, you factorize and solve for x. And then use those values of x to find the y value at the stationary point. You take same values of x to find the y values at stationary point. Remember that this is our gradient. This is our y. G at x is our y, and then this is